Chemical Kinetics Part 6, presented by G. Satyanand Gaur, Assistant Professor, Department of Chemistry, Dr. B.R.R. Government College, Jayacharla. In this discussion, we learn about the complex reactions and the collision theory of reaction rates. Let us see the details of complex reactions. Complex reactions are classified into 4 types. One, reverse or opposing reactions. Second is parallel, competing or side reactions. Third is consecutive reactions. Fourth are chain reactions. These are the types of complex reactions. Let us discuss about the reverse or opposing reactions. Let's consider a reversible reaction. A gives B. A convert into B in the forward reaction and B convert into A in the backward reaction. So it is a reversible reaction. The rate constant of forward reaction is given by K1, whereas the rate constant of backward reaction is represented by K minus 1. Both of these forward and backward reactions takes place simultaneously. In this reversible reaction, in order to achieve the equilibrium, what is the condition? The condition is the rate of forward reaction must be equal to rate of backward reaction. That we know. Means when the rate of forward and backward reactions becomes equal, then the equilibrium will exist in the system. For example, in this reaction, the initial concentration of capital A reactant is small a, and the concentration of B is 0. When time is equal to 0, they are the concentrations. The reactant concentration is A, whereas the product B concentration is 0. Now the reaction has takes place for T time. In this time T, X amount of reactant is consumed. So what is the remaining concentration now? The remaining concentration will be, it is A minus X. The remaining concentration of A will be A minus X, means at time T if we observe the concentrations of reactant and product, A minus X is the concentration of reactant and X will be the concentration of product. So here two reactions are taking place simultaneously. They are the forward and backward reactions. That's why the rate of reaction will be equal to the difference of rate of forward reaction and rate of backward reaction, because these two reactions are taking place in opposite directions. So net rate of reaction will be equal to rate of forward reaction and rate of backward reaction. What is the reactant for forward reaction? Capital A is the reactants. That's why the rate of forward reaction is represented as minus D concentration of A divided by dt. So what will be the reactant for backward reaction? B acting as the reactant for backward reaction. That's why it is D of B divided by dt will be equal to, that is rate of backward reaction. Rate of backward reaction. But to calculate the difference, it is not equal to, that is the difference, it is minus difference you have to write, is it? So the difference of this one, both of these are, we are calculating the difference. In order to calculate net rate, it is K1 into A minus K minus 1 into B. Here also we can write a minus. So minus D of concentration of A divided by dt minus D of concentration of B divided by dt is equal to K1 into concentration of A, because the rate of forward reaction is directly proportional to concentration of A, whereas the rate of backward reaction is directly proportional to concentration of B. So rate of forward reaction will be equal to K1 into concentration of A, whereas rate of backward reaction will be K minus 1 into concentration of B. So difference we are calculating K1A minus, that is K minus 1 into B. So we are saying that X moles per liter of reactant is reacted in time T. Then the net rate will be equal to dx divided by dt. It It is represented by dx divided by dt. That is equal to K1 into A minus X, because this is the concentration of A after time t, minus K minus 1 into X is it. So what is the concentration of B at time t? Here we know that. It is K1 into A minus X minus K minus 1 into X. So this represents the overall rate of reaction, means we say it is net reaction. It is the difference of the rate of forward reaction and backward reaction. Okay, here we express this K1 and K minus 1. That is, we calculate K1 and K minus 1 in terms of equilibrium concentrations. Let's see the details. So at equilibrium, what happened? The net rate becomes equal to 0. Why the net rate becomes equal to 0? Because the rate of forward reaction will be exactly equal to rate of backward reaction. That's why the net rate becomes 0. And the concentration of B, what we said, it is X at a time t, but when equilibrium is reached, X becomes equal to Xe. Let us substitute this. Where dx by dt is equal to 0 means the net rate is 0. So K1 into A minus Xc minus K minus 1 into Xe. What is Xe? Equilibrium concentration of B, or the concentration of A which is consumed in the reaction when the equilibrium is reached. That we say it. So K1 into A minus Xe minus K minus 1 into Xe, we say it. Okay, since it is 0, so we can shift this. So then what happened? This equation converted K1 into A minus Xe minus K minus 1 into Xe. What is Xe once again? It is the concentration of B at equilibrium, or the concentration of A consumed in the reaction when the equilibrium is reached. Okay, so from this equation, now you are writing equation for what? K minus 1. So you can see here K minus 1 is equal to K1 into A minus Xe by Xe. Just you are shifting this Xe in this direction. You are shifting the Xe in this direction. So that we will get equation for just you shift the K in this direction. So what happened? It is K1 into A minus Xe divided by Xe. That is the equation. So this is the equation for K minus 1. Now, in order to evaluate the value of K1, let's substitute this K1, the K minus 1 in equation number 1. Do you know what is meaning of equation number 1? This is the equation number 1. Okay, in this equation, what we are substituting the value of K minus 1. So when you are substituting the value of K minus 1, it is dx by dt. So this is the equation number 1. Here we are represented again, equation number 1. So equation number 1 is dx by dt is equal to K1 into A minus X minus K1 into X. Instead of K minus 1, what we are writing now? K1 into A minus Xe by Xe we are writing. So instead of K minus 1, here you see, instead of this K minus 1, now you are writing this value, which we obtain above it. Yes, we are introducing this value. Instead of K minus 1, you are introducing this value in this equation. So dx by dt is equal to K1 into A minus X minus K1 into A into Xe divided by Xe into X. So dx by dt is equal to, after simplifying this equation, what we get? K1 into Xe minus X into A by Xe. LCM will be Xe, so that we can simplify this equation. Dx by dt is equal to K1 into Xe minus X into A minus Xe. Okay, next let me see the further process, that is Xe by A into dx by Xe minus X is equal to K1 into dt. Means what you are doing here, you are shifting the concentration terms towards one side and time towards another side. Means you are writing this value, you are shifting this equation in the towards LHS and dt towards RHS. Yes, this towards LHS because concentration terms, and you are writing this dt towards RHS. Just rearrangement, that's all. And rearranging this equation, what you get, you see xc by a into dx by xc minus x is equal to k1 into dt. Now we are integrating this equation within the limits of 0 to x and time 0 to t, because x is a concentration of B formed when the time reaches to t. 0 is the concentration of B in the beginning when time is equal to 0. When time is equal to 0. So integrating this equation within these limits, what are the concentration limits? 0 to x, Sxc by a, integral of 0 to x dx by xc minus x, that is equal to k1 into integral of 0 to t into dt. Okay, so from this what we get, it is we get what xc by a log xc divided by xc minus x, means after substituting the proper limits, is it xc by a log xc divided by xc minus x is equal to k1t, or k1 is equal to xc by at, just to shift this t this side. So k1 is equal to xc by at log xc divided by xc minus x, that we get is. This is a representation for k1. Means we are expressing the value of k1 in terms of equilibrium concentrations. But at equilibrium, what is the condition? K1 into A minus Xc minus K minus 1 Xc is equal to 0, because the rate of forward reaction becomes equal to rate of backward reaction. So substituting this K1 in this equation, you are substituting this K1, you see, this instead of this K1, you are substituting this value. So we are substituting K1 in this. So after substituting K1 in the equation, we get Xc into A minus Xc by At log Xc by Xc minus x minus K minus 1 into Xc is equal to 0. This is the equation. After substituting K1, means instead of K1, we have substituted, see, instead of K1, what we have substituted? This is Xc by At log Xc by Xc minus x, we have substituted. So that we get this equation, is it? Or we can write this equation, means you are shifting this K minus 1 Xc into RHS. After shifting K minus 1 into towards what RHS, you will get this final equation. Just you are shifting K minus 1 Xc into RHS. So remaining part will be same. Okay, now you can see K minus 1 representation. From this you can write the equation for K minus 1. Just simply you have to substitute, or you see Xc and Xc will get cancelled. When Xc and Xc will get cancelled, is it? Yes, Xc and Xc will get cancelled. What is K minus 1? A minus Xc by At log Xc by Xc minus x. We are saying this is equation number 3. But at equilibrium, K equilibrium is equal to K1 by K minus 1, means the equilibrium constant is equal to rate constant of forward reaction divided by rate constant of backward reaction. You know the value of K1 and you know the value of K minus 1. What is the value of K1? You see, the K1 value is, it is Xc by At log Xc by Xc minus x. What is K minus 1? A minus Xc by At log Xc divided by, that is Xc minus x. Means we are substituting this K1 and K minus 1 in order to calculate the equilibrium constant. After substituting, these terms will get cancelled. That is log Xc by Xc minus x will get cancelled, log Xc by Xc minus x. Similarly, At and At will get cancelled. Finally, what we get? K equilibrium is equal to, that is Xc by A minus Xc. Like that, we can calculate the equilibrium constant of a reversible reaction when the equilibrium is reached. In this, A is the initial concentration of reactant, where Xc is the equilibrium concentration of product. Equilibrium concentration of product. So if we know these two values, so that you can calculate the K equilibrium. It is calculated from this equation K1 by K minus 1. Mean from the discussion, what we learned? We have calculated K1 and we have calculated K minus 1, and by calculating the ratio of K1 and K minus 1, we are calculating K equilibrium. Is it clear? So this is about the kinetics of what we say reversible reaction. Let's see the second, parallel reactions. What is parallel reaction? The reaction in which the reactants will simultaneously forms different products by different reactions. So in this reaction, the reactant substance follows two or more paths to give two or more products. You see, the preferential rate of such reaction may be changed by variation of pressure, temperature and catalyst in different paths. For example, you see A is a reactant. A simultaneously forming two products is it in different reactions. One is, we say it is A gives B. Second is what? Second is A gives B the first reaction. In the same way, the second is it is forming A gives C. When A is converted into B, what is the rate constant? It is K1. Where A converted into C, the rate constant is K2. There are two rate constants, is it K1 and K2. There are the reactions which takes place parallelly and simultaneously. That's why these reactions are called parallel reactions. So in this, what happened? The reactant substance follows two or more paths to give two or more products. Such reactions are called parallel reactions. Now we have to calculate the total rate of disappearance of A here. What is the total rate of disappearance of A is consumed in both of these two reactions. So we say it is R1 plus R2. That is the rate of first reaction plus rate of second reaction. For both of these, capital A is the common reactant. That way what we write, K1 into concentration of A, K1 into concentration of A and K2 into concentration of A. That's why minus D of concentration of A divided by dt is equal to K1 plus K2 into concentration of A, because concentration of A term is constant in that. That is common in that. Here A term is a common. Just to write A term, concentration of A as common, so that you will get this equation. So overall rate will be equal to minus D of concentration of A divided by dt. That is equal to K1 plus K2 into concentration of A. That is the overall rate of a reaction, we say it is. Next, integrating this equation. Now we are integrating that equation from A to A minus x within the time interval of 0 to t, is it? 0 to t. So integral of D of concentration of A divided by concentration of A is equal to K1 plus K2 integral of dt. What are the limits? When the time is 0, the concentration of A is small a. When the time reaches to t, the concentration decreases to what? A minus x. Means x amount of reactant is consumed in the reaction to form the products simultaneously. Is it? So it is in the form of dx by x. Dx by x means what? It is log x. So by substituting the upper and lower limits, we get what? Log a by a minus x is equal to K1 plus K2 into integral of dt from limit 0 to 2 means we get t. Log a by a minus x is equal to K1 plus K2 into t. Is it? So K1 plus K2 is equal to 1 by t. Just you are writing equation for this, log a by a minus x. You are writing equation for K1 plus K2. So K1 plus K2 is equal to 1 by t log a by a minus x. So from this you can write what again log a by a minus x is equal to what happens? See, from this equation or from this equation you can get this. We are writing the representation for log a by a minus x. So log A by A minus X is equal to T into K1 plus K2. Same is represented here, is it? Same. Both of these equations are same. From that, suppose if you are writing equation for A by A minus X, you are writing a representation for A by A minus X. So A by A minus X becomes equal to e power T into K1 plus K2. Or A minus X will be equal to, what is A minus X? Do you know? It is the amount of reactant A left after time T. That is equal to A into e power minus T into K1 plus K2. This is a relation between the concentration of reactant left over after time T and the initial concentration. Initial concentration, is it? Next, like this we can derive the representation, a relation between the existing concentration and initial concentration in parallel reactions. And also you can calculate the ratio between the rates of these two reactions. What is the ratio? You see, R1 is equal to K1 into concentration of A, R2 is equal to K2 into concentration of A. Suppose if you are calculating the ratio of R1 by what you say R2, then what you get? It is simply you will get K1 divided by it is K2 you will get, is it? Like that you can also calculate the ratio between the rates of these parallel reactions. R1 by R2 becomes equal to K1 by K2 because the concentration term of A will get cancelled. There is it. This is about the parallel reactions. So, what are the examples of parallel reactions? Nitration of benzene, bromination of benzene. In organic chemistry, we see many reactions, is it? Yes. Next, we see the details of consecutive reactions or sequential reactions. Consecutive reactions means in the first reaction a product will be formed, again that product will participate in the reaction to form another product. Like that, a product formed in a reaction again act as a reactant for the next reaction. The type of reactions are called consecutive reactions or sequential reactions. Means in this we can see the intermediate products. The intermediate product will act as a reactant for the next reaction. Final product is formed through one or more intermediate steps, is it? The final product is here C in this representation. A gives B, B is the intermediate. Again B is converting into C. B is the intermediate. So the final product is formed through one or more intermediate steps. Such reactions we call them as consecutive reactions. Consecutive reaction we say. Let's consider this reaction. A gives B. During this reaction, the rate constant is K1. Again B gives C. The rate constant is K2. Now at time T, in the beginning of the reaction, we are saying concentration of A naught, because this represents the time. A naught is the concentration of A. What about B and C? They are 0. Not yet formed in the reaction. When the time reaches to T, let's say the concentration of A is now this A. Concentration of B is represented by this one. Concentration of C. These are the concentrations. They are the concentrations at a time T. From this we easily know that A plus B plus C will be equal to what? Totally A naught. So A naught is equal to A plus B plus C concentrations. This type of relation we see in consecutive reactions. We can also graphically represent the consecutive reactions, how the concentrations of the intermediates and the reactant and the product that will we can observe through the graph. You see the first reaction here. What is happening? A is converting into B, is it? That is, A is converting into B. A is converting into B. Then B is converting into C. Is it? For first one, it is K1 is the rate constant. For second, what you are writing, it is K2 is the rate constant. Now we write minus d of A divided by dt for first reaction. For first reaction, minus d of A divided by dt is equal to K1 into A. Okay. first reaction, we are writing the rate. But what about the second reaction? When you are observing the amount of B in the reaction, when you are observing the amount of B in the reaction, the B is formed in the forward reaction, the first reaction, and B is consumed in the second reaction. You see, formation of B is taking place in the first reaction where the rate constant is K1, and consumption of B is taking place in the second reaction where the rate constant is K2. That's why D concentration of B divided by dt will be equal to K1 into concentration of A minus K2 into concentration of B. So formation of B and consumption of B. That's why we are calculating the difference. We are calculating the difference. So the concentration of B, the rate of consumption of B or formation of B at any time will be equal to D of concentration of B divided by dt. That is equal to K1 into concentration of A minus K2 into concentration of B. Similarly, observe about C. Only it is forming in the second reaction. That's why we write K2 into concentration of B. Because for second reaction, B is the reactant. So we can write formation of C in the reaction. Formation of C will be equal to, that is D concentration of C divided by dt, that is equal to K2 into B we write it. And also you will observe how the reactants and products and intermediate concentrations are changing with time. On x-axis and y-axis, concentration is taken, and x-axis we have taken what? Time. Let you observe the concentration of A first again. Again I am writing, you see, A is converting into what? B. Again B is converting into what? C. Let you observe the change in concentrations here. Change in concentrations. How the concentrations are changing. In case of A is totally consumed in the reaction. When the reaction is completed, what happened? The total A will be consumed. That's why in the beginning concentration of A will be maximum. Gradually what happened? The concentration of A gradually decreases with time. Finally it reaches to 0. Is it? This one A. It represents about A. In the beginning it will be maximum. Gradually it will consume in the reaction and reaches to 0. What about B? It is forming in the first reaction and consuming in the second reaction. When it is formed in the first reaction, gradually what happened? Its concentration increases with time. After some time what happened? Again it will consume in the next reaction. That's why its concentration decreases. This is about the B. In the first reaction it will form. Gradually it will form and reaches maximum. And again it decreases. Why? Because the B is participating in the second reaction. It is converting into C. What about C? In the beginning C will be 0. C will be 0. This is the final product. That's why the concentration of C gradually increases. This is forming in the second reaction. From B gradually increases. So graphically we can represent the variation of concentration of reactants and products in a consecutive reactions. Okay, next chain reactions. What is the meaning of chain reaction? A reaction in which highly reactive species are produced as intermediate, which carry out the reaction at a rapid rate for a long time. Means the species which are formed in the reaction as intermediate will attack many other reactant molecules and form the product. The reaction may sometimes becomes violent. So these intermediates will carry out the reactions at a rapid rate for a long time. Many species will one by one that will participate in the reaction. The type of reactions we call chain reaction. The chain reactions include the following steps. The one is chain initiation step, we say. Chain propagation step, second one. Chain termination step is the third one. So chain initiation step, chain propagation step, chain termination step. The three steps involved in chain reaction. Example for chain reaction, we say photochemical reactions of hydrogen and fluorine, and also hydrogen and bromine. and etc. Let me see the details of hydrogen and chlorine. What is the chain initiation you see? The chlorine molecule is undergoing what homolytic cleavage to form the free radical. Chlorine free radicals are forming in presence of light. It is taking place. It is a photochemical reaction. In presence of light, the chlorine molecule is homolytically dissociating to give chlorine free radicals. Now the propagation will start. This chlorine free radical again will participate in the reaction now. The chlorine free radical is participating in the reaction. It attacks the hydrogen molecule in the reaction mixture to form HCl and H dot. Means hydrogen free radical is forming. Again this hydrogen free radical will attack chlorine molecule to give HCl and Cl dot. Means in propagation you can see a recurring formation of free radicals are taking place. Recurring formation of free radicals are taking place. Just by formation of one chlorine free radical, it is generating hydrogen free radical and also another free radical of chlorine. That's why this reaction will proceeds for a long time. Termination. If any two free radicals are combining with each other, then what happens? The termination will take place. So termination of this reaction takes place on the walls of container. M is the metallic surface or walls of container. Cl dot plus Cl dot gives Cl2. H dot plus H dot gives H2. H dot plus Cl dot gives HCl. There are different possibilities we are writing. Like this, in any chain reaction, 3 steps will be involved. And the chain initiation, chain propagation, and chain termination. They are the complex reactions. What was the first one? The first complex reaction is reversible reaction. What is the second one? The second one was a parallel reaction. The third one is consecutive reactions. Fourth one is chain reactions. We have seen the details of these reactions. Okay, this is about concept of complex reactions. Let me discuss about the collision theory of reaction rates. This is applicable to the gaseous molecules where two gaseous reactants are present in the system, is it? Suppose A and B are there. A and B are the gaseous substances. Now both of them are allowed to react in a container. Okay, so in 1 second, how many collisions will take place between these two? 10 power some 15 to 32. 10 power 15 to 10 power 32. Number of collisions will take place in 1 second. If all these collisions between the reactant molecules produces a product in the reaction, so that the reaction may complete in fraction of time. But in many reactions, we cannot see this. We will not observe this rapidness. Means some reactions are taking place slowly, some reactions are taking place very fast. Some reactions are with medium velocity. So this collision theory of reaction rates will explain why the rate of reaction is not equal to the number of collision takes place between the reactant molecule per unit time. Okay, so in order to occur a chemical reaction between, that is a reactant, in order to occur a chemical reaction between the reactant, what is mandatory? The collision must take place between the reactant molecules. The reactant molecules must collide with each other. But all these collisions are not effective. Remember, this is very important. All collisions are not effective, means the collisions which are taking place between these reactant molecules will not produce the products at all times. So which collisions will form the products? The collisions which occur between the reactant molecules which possess a minimum energy, they only form the products in the reaction. Means among the number of collisions, only a small fraction of molecular collisions, only form the product in the reaction. The reactant molecules must collide with proper orientation. Second point is. So 2 points are playing important here. The molecule which possesses minimum energy, which is called what? Threshold energy is it. Threshold energy can only form the products in the collision. And the reactant molecules, which are the reactant molecules, must collide with proper orientation. These 2 points are important. So among the reactant molecules, all molecules will not possess the minimum energy, which is called threshold energy. Among the reactant molecules, only few molecules will contain or possess threshold energy. They only form the products in the reaction. What is the second one? The second one means when these collisions are taking place between the molecules, these collisions may or may not take place with proper orientation. So in order to form the reaction, in order to form the products in the reaction, 2 points are important. One is the reactant molecules must possess a minimum energy, which is called threshold energy. Threshold energy. What is the second one? The second one is the collision must take place with proper orientation. That's why the rate of chemical reaction is usually slow because of these 2 points. Because of these 2 reasons, the rate of reaction will be generally slow compared to the number of collisions taking place per second. Means if you compare the number of collisions taking place per second and rate of reaction, the rate of reaction will be generally less. Next, you see this case. Let's consider a gaseous reaction. A plus B gives AB. A and B are the gaseous reactant molecules. The number of collisions taking place between A and B per unit volume in unit time is represented by ZAB. We are saying it is ZAB. What is ZAB? It is the number of collisions taking place between the reactant molecules A and B per unit volume per unit time. So from Maxwell distributions of velocities, Maxwell relations, we say ZAB, there is a number of collisions taking place per unit volume. ZAB is given by 8 RT by pi mr power half pi sigma square Na into Nb. In this, what is this mr? It is reduced mass. If Ma and Mb are the masses of A and B respectively, then we say reduced mass will be equal to, it is Ma Mb divided by Ma plus Mb. Like that we calculate it. So ZAB is equal to 8 RT by pi mr power half into pi sigma square Na and B. Na and B are the number of A and B molecules per unit volume. Sigma is the distance of closest approach. That is, we say the distance between the nuclei of A and B, like that. R is the universal gas constant. So what is ZAB? ZAB is the number of collisions per unit volume taking place per unit time. We know that all these collisions represented by ZAB will not form the product in the reaction. Only the molecules with minimum energy will result the products in the collisions. Now these collisions which form the products are called as effective collisions. Is it all these collisions are not effective? Only some collisions are effective. Which collisions are effective? The collisions which are taking place between a reactant molecule that possesses threshold energy, that is called minimum energy. Now the effective collisions are given by, that is ZAB into F. Means among all these collisions, a fraction of collisions only form the product. That's why the effective collisions will be equal to what? ZAB into F. F is a fraction of molecule that possesses activation energy or threshold energy, we say. Now this ZAB into F only equal to rate of reaction. Do you know F is not equal to 1? F will be less than 1. F is equal to no, if F is equal to 1, then what happens? All collisions that takes place between the reactant molecules are forming the product. But generally we observe this F is less than 1 in many reactions. That's why the number of effective collisions would be equal to ZAB into F. You clear? What is ZAB? ZAB is the number of collisions taking place between A and B in a unit volume per unit time. All these collisions will not form the product. Which collisions will form the products? Only that is ZAB into F. What is the small f? It is a fraction of molecules that possess what? It is a fraction of molecules that possess activation energy. According to Maxwell distribution law, this F will be equal to Ne divided by N. What is Ne? It is the number of molecules having activation energy. N is the total number of reactant molecules. Ne divided by N. So according to Maxwell distribution law, this is equal to e power minus Ea by RT, where Ea is the activation energy we know, R is universal gas constant, T is absolute temperature. So substituting the value of F in ZAB into F, we get this equation. So the number of effective collisions now is equal to ZAB into e power minus Ea by RT. Now this is equal to what? Reaction rate. So we write the reaction rate is equal to ZAB. What is ZAB? This is the ZAB. The number of collisions taking place per unit time between the reactant molecules. 8 RT by pi mR power half pi sigma square NA/NB. What is F? F is e power minus Ea by RT. This is nothing but the reaction rate. Reaction rate, which is equal to the number of effective collisions. Number of effective collisions. But what is reaction rate? Which is directly proportional to concentration of reactant. That's why reaction rate is equal to K into concentration of A into concentration of B. Ca and Cb are the concentrations of A and B respectively. Or we write it is K into a number of molecules of A, number of molecules of B present in 1 liter. So the reaction rate K into Na and B, because the reaction rate can be written like this. K into Na and B is equal to, this is the value of Z, is it? And whereas this is the value of F, ZAB into F. ZAB into F. Now we can cancel this. Na and B will get cancelled. Here also Na and B will get cancelled. Finally what? We get K is equal to 8 RT by pi mR power half into pi sigma square e power minus Ea by RT. What are the units here? You see, cubic centimeter, molecule inverse and second inverse. In order to convert this into meter cube into mole inverse, second inverse, we have to divide this equation by 6.023 into 10 power 23 divided by 1000. With this term you have to divide it. This equation has to be divided in order to convert the units from cubic centimeter, molecule inverse, second inverse to meter cube to mole inverse and second inverse. Is it? You have to divide it with this term. Right, next, so we can write this equation as, equation number 1, this equation can be written as in the form of A, means it's just we are leaving this t power half term, and remaining part in this remaining part except t power half, remaining part is represented by capital A, which is called frequency factor, into t power half. Here is t power half to e power minus Ea by RT. So K is equal to A into t power half d e power minus Ea by RT. So the value of K calculated from this equation is in agreement with exponential values in many reactions. Collision theory of reaction rate successfully explained the reaction rates of bimolecular reactions that takes place in gaseous state. Okay, so finally K is equal to what we get? The finally is equal to, finally K is equal to A into t power half into e power minus Ea by RT. Next you see, not only the frequency factor, not only the F, another factor, that is what? Orientation factor. That is also a steric factor. That also plays important role in effective collisions. So what we say, another additional factor is what steric factor is. Steric factor or orientation factor of colliding molecules is also very important. So the orientation or probability factor P is related to entropy of activation introduced in the above equation. Means not only A, we have to write T also. So this is somewhere spelled wrong. You see, P into, here what we have to write T power, that is what we have to write P into capital T power half, you see, into A, next into e power minus EA by RT. E power minus EA divided by what we write, it is RT. This will be the final equation, isn't it? P into T power half. Here T power half also have to write T power half. Okay, let me write this clearly. Here under term we have to include what is that, T power half should be there. And whereas this e power minus EA by RT, this is the power of small e. So P into T power half into A into e power minus EA by RT, where P is the probability factor or orientation factor. That should be introduced in this one. The collision theory of reaction rate that's in this way describes simple bimolecular reaction as model. Means according to collision theory of reaction rates, all reactant molecules which are colliding with each other per unit volume per unit time will not form the products. Here two important points has to be considered. One is the collisions between activated molecules. Second is the probability factor. That is the orientation or probability factor. These 2 points are very important, and these 2 points will control the rate of reaction. Okay, this is about collision theory of reaction rates. Thank you.